Hi, I'm Josh Lovell, Product Line Manager for Teledyne ISCO's pharmaceutical R&D products. Thanks for joining our regular chromatography webinar series. Today's topic is an introduction to flash chromatography. We are excited to present Dylan Cavey, one of our in-house application specialists in Lincoln, Nebraska. Dylan works in the lab with our flash and preparative HPLC SFC systems, supporting engineering and developing applications based on customers' needs. Dylan will be presenting about the top 5 essentials to maximize success in Flash. At this point, it's my pleasure to hand it over to Dylan.
Thanks, Josh. Thanks everyone for attending today's webinar. Today we're going to talk about an introduction to Flash chromatography, the top 5 essentials to maximize success in Flash. I'm Dylan Cavey. I'm an applications chemist here at Teledyne ISCO. Before we begin, I would like to point out that there is going to be a Q&A section at the end of today's webinar. So if a question comes to mind, don't be afraid to type that into the question box below, and I'll try to answer those questions as best as I can at the end of today's webinar. Here's our overview for today's webinar. Before we can get into the top 5 essentials to maximize success in Flash, first we have to ask the question, what is Flash chromatography, and how does chromatography even work? So we're going to give a bit of a background to start, and we'll also talk about the advantages of using Flash. Then we'll dive into the top 5 essentials, starting with the stationary phase. We'll talk about some different chemistries that go along with the stationary phase. We'll hit column efficiency and also column care. Then we'll transfer on to the mobile phase. We'll talk about the difference between normal and reverse phase. We'll also talk about modifiers and how adding these modifiers can give us better resolution. Then we'll talk about method development. We'll talk about going from TLC to Flash, and we'll also talk about isocratic versus gradient and step gradients and all those different methods and what's the benefits for using those different methods. We'll talk about sample loading, liquid versus solid loading, the benefits for each of those. Then lastly, we're going to talk about the focus gradient generator, which is now available on our Combi Flash Next Gen units. I'm going to tell you how to use it and why you should be using it. So what is flash chromatography? Before we can answer the question of what flash chromatography is, first we need to understand how chromatography works. So with that, I'm going to get a little bit of help from our Teledyne ISCO chromatography mascot, Reddy the raccoon. So you're going to see a lot of Reddy throughout today's webinar. But what is chromatography? Well, in simple terms, chromatography is just the process used to separate different components of a mixture. A lot of time this is going to be a couple different compounds, but it could also just be A and B, and you want to get the best separation between those two as possible. We're also going to talk a lot today about the stationary phase, and it's actually one of our top 5 essentials to maximize success in Flash. But what is the stationary phase? Well, the stationary phase is exactly what it sounds like. The stationary phase is stationary. This is the phase of chromatography that the components of a mixture have to travel through, and this is what's going to generate our separation. Now, different stationary phases are going to have different chemistries, and with different chemistry comes different affinities. So what do I mean by affinities? Well, I like to think about it in terms of ice cream. So let's say you have some chocolate lovers, but you also have vanilla lovers. So we have a chocolate ice cream store. It only sells chocolate ice cream. Well, it's going to be really hard to remove a chocolate ice cream lover from that store. It's going to be a lot easier to remove a vanilla ice cream lover from that store. So their chocolate lovers and the vanilla lovers are going to have different affinities for that ice cream store. Just like our different compounds. If we have a polar compound, it's going to love a polar stationary phase. But if we have a non-polar stationary phase, that polar compound's not going to like it as much. A saying to remember is like likes like. So a polar compound is going to like a polar stationary phase. A non-polar compound is going to like a non-polar stationary phase. We're also going to talk about mobile phase. And again, the mobile phase is exactly what it sounds like. This part is going to be moving. This is the phase that's going to carry and move components of a mixture throughout the stationary phase. Now that we have some definitions about chromatography, let's use an analogy to better illustrate how chromatography actually works. So in our analogy, we're going to look at a residential street on trash day. The trash cans are going to act as our stationary phase, and the street is going to act as our mobile phase. Ready is going to be our compound of interest. This is what we want to separate. And Reddy once told me that the smellier the trash, the better. That's where all the goods are, is in the smelly trash. Normal or good smelling trash, it just doesn't have as good as food in there. So let's say we have a neighborhood and they really take care of their trash. They use those scented trash bags, they use lots of Febreze, they just want their trash smelling good. They want to have a good smelling neighborhood. Well, if Reddy's in that neighborhood, he's not going to interact much with the stationary phase. He's not going to look in those trash cans because they smell good. He doesn't like that. So he's going to stay on the street. He's going to stay on the mobile phase looking for worse smelling trash. So he's going to fly down that road hoping to find a worse smelling trash can. Now let's switch that. Let's say we have a neighborhood who just had a fish fry and everyone had eyes that were bigger than their stomach, so they had to throw away a lot of fish and it's just been sitting in their trash cans for a week. Well, those are going to reek, and Reddy's going to love that. He's going to want to interact with each and every single one of those trash cans. At the same time, there's a bear walking down the street, and the bear is a lot like us. He's appalled by those trash cans. They smell so bad. So he's not going to interact much with that stationary phase. He's not going to interact much with those trash cans. Instead, he's going to stay in the mobile phase. He's going to stay on the street, walking down the street looking for just better food options. So as they make their way down the street, Reddy's going to spend a lot more time interacting with the stationary phase. He's going to spend a lot more time walking down this residential street. So the bear's going to exit the street first, and then Reddy's going to slowly make his way. And this is how chromatography works. Different compounds are going to elute at different times based on their affinity for the stationary phase. So Reddy here has a strong affinity for smelly trash, or that stationary phase. Now that we know how chromatography works, we can finally answer the question of what is flash chromatography? Now, before flash chromatography, there was gravity chromatography. And gravity chromatography is exactly what it sounds like. It used gravity to pull the mobile phase through the stationary phase. So this was very time consuming. And it also didn't give very good resolution. And resolution is just the separation between your two different compounds. So compound 1 would elute off your column, and then compound 2 would be right behind it. It was also a manual process, so you constantly had to be there and check on things to make sure that it was running well. So it's about as much fun as watching paint dry. Watching your mobile phase trickle down your stationary phase isn't much fun. This is where William Clark Still and his colleagues at Columbia University came in. They created flash chromatography in 1978, and what they did was they added compressed air to the mobile phase. So you can see that on the diagram on the right. So the compressed air was able to push that mobile phase through the stationary phase. So this was completely automated, so you didn't have to be there anymore. You didn't have to watch every single step. It was a lot faster because now you're using compressed air instead of gravity. It was also inexpensive compared to other methods, and it also required minimal development time. Now that we have a good understanding of what flash chromatography is and how chromatography works, we can finally get into our top 5 essentials for maximizing success in flash chromatography. And I know you guys have all been dying for this moment. So we're going to start off with our first essential, and that's going to be our stationary phase. So as I mentioned earlier, different stationary phases are going to have different chemistries. And here at Teledyne ISCO, we have plenty of different ready-set stationary phases to choose from. If we look at the chart on the left, this chart is decreasing from top to bottom in polarity of stationary phases. So at the top, you're going to have the most polar stationary phases. These are your silica, your alumina, your amines, and these are most commonly going to be used in normal phase conditions. As we work our way down that chart, we're going to get into our reverse phase stationary phases, and we'll get into the difference between normal phase and reverse phase a little bit later in our essentials. But these reverse phase stationary phases are normally carbon chains, C8 or C18. Those are just the amount of carbons within that carbon chain. One thing I would like to point out is why you should use a C8 instead of a C18. A C18 is going to be the most popular reverse phase stationary phase, but why might you want to use a C8? Why might you want to use a C18AQ? Well, you might want to use a C8 stationary phase compared to a C18 stationary phase based on pore size. So as you can imagine, the C18 is a larger carbon chain, so the pore size is not going to be as big as compared to the C8. So if you have a large compound of interest and you're using reverse phase, you might want to look at a C8. That might give you better resolution. Same could be said for looking at a C18AQ. The problem with C18 is that those large carbon chains are so hydrophobic that you can't really use a lot of water in your solvent systems. If you do, you're going to run into phase collapse, and that's what we see here on the left, is these carbon chains in aqueous conditions like to bundle up together. The water pushes them together. Again, likes. So they're going to like the other nonpolar carbon chains and they're going to bundle up together. So this is going to create voids in your column, and your compound of interest is able to just run right by those carbon chains when they're all pressed together, and it's not going to interact much with the stationary phase. This is where C18AQ comes into play. C18AQ has these R groups in between the large carbon chains, and these are hydrophilic, meaning they love water. So they're able to interact with the water, and this is able to keep those C18, those large carbon chains, extended within the column, so they're still able to interact with that compound of interest. So you might be wondering which stationary phase you should choose. And a lot of that comes down to your compound of interest and what properties it holds. Is it charged? Is it polar? Is it nonpolar? Does it have acidic or basic properties? Well, this flowchart is really helpful when deciding which stationary phase to use. So let's say you have a low polarity compound. Well, you might be looking at normal phase in that area. You might want to use silica gel. One thing I will note about this flowchart is the yellow blocks are our Ready Set Gold high performance columns. So these stationary phases are going to be spherical in shape instead of irregular, and they're also going to be a smaller diameter, so you're able to fit more into one column. So that leads us into our next slide. Let's talk about column efficiency. So what makes a column more efficient? Well, a lot of that's going to come down to the particle shape. Is it spherical or is it irregular? If we look at the graphic on the right, we can see how much better spherical shaped media is able to pack a column compared to irregular. So this is going to lead to better column packing. It's going to be more dense, and it's going to increase your efficiency because the more media you're able to fit in a column is going to increase your surface area. And if you increase your surface area, that's going to increase the chances of your compounds interacting with that stationary phase. A couple things to keep in mind when working with irregular is, yes, you're going to lead into less dense packing, but you can also create fine particles. So some of these irregular shapes are going to have really, really tiny pieces that can break off due to the pressure from your mobile phase, and those can get swept up into your chromatography machine, which can lead to problems down the line. Another thing that's going to increase column efficiency is decreasing your particle size. So the smaller the particle size, the better. And this again goes down to surface area. The smaller the spherical shape of your media, that's going to increase your surface area, again increasing the chances of your compound interacting with that stationary phase. Now let's look at an example on our two different types of media here at Teledyne ISCO. Our Ready Set Gold, as we mentioned on the previous slide, is our high performance columns. These are spherically shaped and they're 20 to 40 microns in particle size. The Ready Set material is irregular and it's also 40 to 60 microns. So if we run a separation on these two different compounds with these two different medias using hexane and ethyl acetate as our mobile phases, you can see that the Ready Set Gold material is able to complete the separation in 24 minutes and it only uses 26.5 liters of solvent. Now if we compare that to the Ready Set material, that's going to take over an hour. It's going to take 64 minutes, and it's going to take 45.7 liters of solvent. So if you have an efficient column with small particle size, spherical shape, you're able to increase your flow rates, which is going to lead to quicker times, and it's going to reduce your amount of solvent. So that's going to save you money, and it's going to save you time. Another thing that you can think about when using higher efficient columns is you're able to increase the amount of sample you load onto those columns. Since it has more surface area, you're able to load more sample onto the column, so you're able to limit the amount of runs you have to do, again saving you money and saving you time. Now let's talk about column care, because if we care for our columns, they're going to care for us back, and they're going to show us love by keeping a couple extra dollars in our pockets. So a couple things to note. Our columns here at Teledyne ISCO can be used 20 times with the proper care and sample preparation completed. Now, each column that we ship out is going to come with specific care instructions, so make sure you read those before your first couple separations. Now, each column we ship out of here is going to be shipped dry, so it needs to be pre-conditioned. It needs to be pre-washed. So if you're working with C18, C18AQ, C8, those need to be washed with 6 column volumes of 1:1 water acetonitrile or 1:1 water methanol. If you're working with the amine columns, those should be washed with a couple column volumes of methanol. Make sure you equilibrate your column before each run. This just gets the column used to the solvent system that you're using. So if you're using 95% water and 5% methanol, you're looking at reverse phase. Have an equilibration volume in there where you're pumping 95% water, 5% methanol. Just get that column used to the solvent system you're using. Sample prep, just be smart with it. Don't add a lot of gunk to these columns, because if you add a bunch of gunk to the top of the column, it can clog that top frit. And if you clog that top frit, then you're going to create multiple different pathways for your solvents to go through and your compounds to go through. So you're not going to see the separation that you want. You're not going to see that resolution that you want, because your compound's just going every which direction. It's not a uniform path for your compound to travel. If you are looking at using like natural products for flash and it's hard to get a compound completely soluble, you might want to look at using a solid load cartridge. And this solid load cartridge can act as a guard column. So a lot of that gunk is not getting onto your top frit of your actual column. It's actually just getting caught in that solid load cartridge. So you don't have to replace your column. You just have to replace your solid load cartridge, or your guard column in that case. Couple post-run care tips. I always like to end my flash runs with 100% of my strong solvent. So that's either methanol in reverse phase, or it's going to be ethyl acetate in normal phase typically. And this is just able to wash anything that's caught on the column out, so it's ready to go for that next run. Storage, never dry out your column. Once you're done using a column, make sure that you put those red caps back on. We always ship our columns with these red caps, one for the top and one for the bottom. So once you finish your run, make sure that those 2 caps are in place, and always make sure that you're using miscible solvents. This isn't going back to elementary school where you want to see water and oil separate. Let's always make sure that we're using miscible solvents. So miscible means that those solvents can interact with one another, that they're not going to separate. It's hard to separate different components of a mixture if your 2 solvents don't want to mix. So always use miscible solvents when storing those. Make sure that they're well capped. You're typically going to look at like 10 to 80% water and 20 to 90% organic solvent. Anything that falls within those guidelines is good. And if you're using any sort of modifiers in your solvent system, make sure that you wash those out, because we don't want to store those under basic, acidic, or any sort of buffered conditions. We will now move on to our second essential for maximizing success in flash chromatography, which is going to be the mobile phase. We mentioned it a little bit before. This is the phase that's going to carry your components throughout the stationary phase. So how do we know which mobile phase to use? And a lot of that's going to come down to which phase you're in. Are you in normal phase, or are you in reverse phase. And what's the difference between those two phases? Well, let's start with a normal phase. In normal phase, you're going to be using a polar stationary phase. Think silica, alumina, amine. And you're going to be using a non-polar mobile phase. So if we look at the polarity chart on the right, you can see that hexane and ethyl acetate are highlighted in purple. And these are going to be your most common solvents when you're using normal phase. You're going to use a combination of hexane and ethyl acetate. So you can see that hexane is extremely nonpolar, and ethyl acetate has a polarity of 4.3. So this is going to make ethyl acetate your strong solvent in normal phase conditions because it's more polar, so it's able to interact more with that polar stationary phase. So it's able to pull more compounds off of that silica, off of that alumina, and off of that amine. So most times you're going to be working with a percent of ethyl acetate in hexane when you're working with normal phase conditions. Now if we play the reverse card and we switch over to reverse phase, the stationary phase and the mobile phase, the polarity of those two are going to be reversed. So now we're going to be looking at a non-polar stationary phase, the C18, the C8, the C18AQ, and we're going to look at polar mobile phases. So now water, methanol, acetonitrile are highlighted in purple on the polarity chart. So in reverse phase, we're actually going to start with the most polar solvent. So most times you're going to have water as your first solvent, and then you're going to either use methanol or acetonitrile as your strong solvent. So the strong solvent in reverse phase is actually more non-polar. So if we look at methanol and acetonitrile, they're going to interact more with the C18, the C18AQ, or the C8. So that's going to be able to pull more compounds off of that non-polar stationary phase. Now there are other solvents than the ones I had just previously mentioned, and these solvents can be categorized into different groups based on their different properties, whether or not they're hydrogen donors, hydrogen acceptors, or if they're large dipoles. So we can use the solvent selection chart to achieve better chromatography. So let's use an example. Let's say we're looking at reverse phase, and we use a certain percent of acetonitrile in water on a C18 column, and we just didn't get the separation we were looking for. Well, one might think that it's a good idea to switch acetonitrile for acetone, both of which are in group 6, but acetone has a polarity of 5.4 compared to acetonitrile 6.2. So acetone is more non-polar. And in this case, in reverse phase, that's going to make it a stronger solvent than compared to acetonitrile. So the hope would be that since you're using a stronger solvent, you're able to pull more compound off of that C18. But the better idea is actually to switch groups, switch the properties of those solvents. So instead of using acetonitrile, you could switch over to group 2 and look at methanol. And methanol is going to act more as a proton acceptor rather than acetonitrile, which was shaded more to the large dipole and hydrogen donor. This is going to allow you to manipulate the C18 more, and it's going to give you a different selectivity in hopes to achieve better separation. We can also use solvent modifiers in our mobile phase to affect the way it interacts with the stationary phase. A common reason you'd want to do this is to affect the pH. A lot of acidic and basic compounds will result in fronting and tailing. So if we want to look at the example on the right, you can see that top chromatogram was using a reverse phase condition with methanol as the strong solvent. And if you look at that second peak, that second compound, you can see a lot of tailing. That compound is just drug out during the elution over several CV. But if we just add just 0.1% TFA, trifluoric acetic acid, to that methanol, to our strong solvent, you can see what that does to that peak shape for that second compound. We're starting to achieve better chromatography with using an acidic modifier. Another thing to keep in mind is that acids will help pronate and keep our compound from H bonding with the silica surface. That's important in normal phase conditions. Another thing to keep in mind is we want to work with low pH to prevent the hydrolysis of the siloxane bond in our stationary phase. Another reason you might want to use a modifier is competing amines. If you have a compound that has a lot of amines, they can hold really tightly onto a silica. So if we add a certain percentage of modifier that contains amines, it's going to compete for that silica spot. So the more amines you add to your solvent systems, the less chance you have of your compound really holding tight to that silica surface. Some common modifiers are triethylamine, abbreviated TEA. That one's used a lot. Ammonium hydroxide, acetic acid, and we already mentioned TFA, trifluoric acetic acid. Now we're on to essential number 3, method development. Now, a common way to find out how your stationary phase and your mobile phase are going to interact with your compound of interest is to run TLC plates. And when we're running TLC plates, we're really curious about what the retention factor of our compound is. So here's an example of us running a compound of interest under normal phase conditions. So the TLC plate on the left is ran with just ethyl acetate. The one in the middle is ran with a hexane ethyl acetate in a 1:5 ratio. And then the one on the right is another hexane ethyl acetate ratio 1:1. So as we develop these TLC plates, you can see how the compound of interest is going to move with the stationary phase and the mobile phase. So for the one on the left, the compound of interest travels 0.95, and the distance the solvent traveled was 1. We're using some pretty simple terms to make the math easy for us when we're calculating the retention factor down at the bottom. That equation can be found down at the bottom of the slide. If we look at the one in the middle, we traveled 0.5, and the one on the right, 0.25. So we can plug these numbers into our equation to determine the retention factor. So for the left one, we're going to get a 0.95 retention factor. The one in the middle is going to be a 0.5 retention factor. And then the one on the right is going to be a 0.25 retention factor. So the compound of interest on the solvent system on the left really liked the mobile phase. The one in the middle liked it about equally between the mobile phase and the stationary phase. And the one on the right actually held on and retained on the stationary phase better than all of the other solvent combinations. Now, actually, we want to have our retention factor at 0.25. That's the retention factor we want for our compound of interest, plus or minus 0.05. So if you have a retention factor from 0.2 to 0.3, that's good method development. That's exactly what we're looking for. Now, there are also some different mobile phase techniques that we need to look at. The first of which being is an isocratic run. An isocratic run is going to keep your percent of solvent B consistent throughout the run, or the percentage of your strong solvent consistent amongst the whole entire run. So in this case, we have an isocratic run at 20% solvent B. So it's going to remain at solvent B throughout the whole entire 20 minutes. We could also run a gradient run, which is going to increase the amount of solvent B as the run continues to go. So it's going to go from 0 to 50% B over a course of 20 minutes. We can also look at stepped gradients, which is just a bunch of isocratic runs with increasing amounts of solvent B throughout the run. Each of which of these techniques has their own advantages. I will mention that an isocratic run can be optimized for any separation. So any compound can be separated with an isocratic run. It might just take a little bit more method development, more time to figure that out, and you might have better success using a stepped gradient or just a linear gradient. Let's look at an example comparing these different mobile phase techniques. We'll look at two different amides, both amide A and amide B. The only real difference between the two amides is that amide B has this aromatic structure. And you can see how that aromatic structure affects its retention when we run a TLC plate in 30% ethyl acetate in heptane. And you can also see the retention factor below the amides' names. So what happens when we try to separate these two different amides using an isocratic run? Well, in this case, we use an isocratic run at 30% ethyl acetate in heptane. And you can see that we get 3 impure fractions. we have some overlap between amide A and amide B, and that's not great chromatography. We'd like to get baseline resolution, meaning that we're going to get pure fractions of each compound and no impure fractions. So in this case, we do get some pure fractions, but not all of them are pure. So let's drop that isocratic percentage, and let's run an isocratic run at 20% ethyl acetate and heptane. Here you can see that we are achieving those pure fractions. We get 11 of each amide. And as I mentioned earlier, isocratic runs might take more method development time, but you can normally always get good separation with an isocratic. It's just going to take time and quite a bit of method development. But we can also run this on a gradient, and we can have a gradient going from 10 to 30% ethyl acetate over a course of 25 minutes. And in this case, we're also going to get pure fractions. But this time there's only 14 pure fractions compared to the 22 we saw previously on that isocratic run. So there's 8 fractions that we're saving. So we're saving time and we're saving solvent. So that's saving you money and time, which is what we're looking for. This is what we're doing to maximize success in flash chromatography. Next, we're going to get into sample loading, whether you should use liquid loading or if you should use solid loading, and some of the benefits for each of those. Why should you be using liquid injection? Well, liquid injection is actually quite simple. All you have to do is load your sample onto the top of the column after equilibration is finished. Now, I will mention that you want to dissolve your sample in the weakest solvent possible. So if we look at the picture on the top right, that sample was dissolved in strong solvent. And that strong solvent is going to pull your compound down the column immediately. So this is going to result in a lot of fronting. But if we dissolve our sample in a weak solvent, like the picture in the bottom right, you can see how much more concentrated that band of your sample is, and that's going to lead us to better chromatography. Another example is if we dissolve caffeine and niacinamide in 100% water, looking at reverse phase conditions. So water is going to be your weak solvent, and we run that on a ReadySep Gold 50 gram C18 column. We're getting really good peak shape, we're getting really good baseline resolution. But if we switch that and dissolve it in 100% methanol, which would be the strong solvent in reverse phase conditions, you can start to see that fronting show up in this chromatogram, and that's not what we want. That's not good chromatography. That can lead to impure fractions. Now, the other form of sample loading you have is solid loading, and solid loading is really good for hard to dissolve samples. It can also increase resolution by extending the length of your column. So in order to demonstrate that, I thought it'd be a good idea to bring Ready and the Bear back. So in this example right here, this is just a column. There is no solid load cartridge. There's no solid loading. And Ready doesn't have very good affinity for the stationary phase. So he's going to fly down this column, and the bear is slowly going to make its way down the column. So we are getting some separation between the two of them. But if we add a solid load cartridge for solid loading, that's going to increase the length of this column. And when we run that separation again, you can see that we're getting even more separation because there's just more length for Ready to run through. And since he's faster, he's going to conquer that distance much more quickly than the bear would. So that's going to result in better resolution between our compounds. You can also minimize band broadening and make sure that we're also drying our sample before we start our runs. And it's a nice thing now because you can actually dry your sample on your Combi Flash systems. All you have to do is hook up your solid load cartridge with your solid load cap, go into manual control and select air purge cartridge, and that's just going to blow a bunch of air throughout the solid load cartridge, allowing you to dry your sample quicker. So why do you have to do that though? Why do you have to make sure that your sample is dried? Well, if you don't dry your sample and you start your run, you're going to see poor chromatography. You're not going to see very good resolution between peaks. If you look at this example here, we're not even getting baseline resolution between these two peaks. But if we dry our sample completely before starting a run, you can see that we're starting to see a lot better peak shape. We actually get down to baseline resolution. So we can use a couple different absorbent materials when we're loading into a solid load cartridge. You can use silica, you can use C-Lite, C18, you can even use boiling chips if you have a synthesis going on and you want to boil some solvent off. A lot of times you might use boiling chips. Well, some of your compounds can be stuck on those boiling chips, so you might as well add those also to the solid load cartridge to increase your recovery. You can use cotton balls and chem wipes if you have a spill in the lab and you need to use chem wipes to suck that up. You can still add those to a solid load cartridge to again improve your recovery. Now we'll get into our fifth essential for maximizing success in flash chromatography, and that is our focus gradient generator, which is now available on our next gen units. Why should you use the focus gradient generator? Well, one of the main reasons is you can get rid of TLC plates. A lot of the time silica TLC plates are going to be available in the lab. But what if you want to look at reverse phase and see how your compound interacts with a C18 media or a C8? Well, those C18, those C8 TLC plates are going to be a lot harder to find within your lab. Another reason why you might not want to use TLC is a lot of the time our TLC techniques aren't up to par. We're not saturating the chamber. My colleague Jack Silver actually wrote a great paper about this titled "Let Us Teach Proper Thin Layer Chromatography Technique." So if you're still interested in using TLC as part of your method development, I'd recommend Google searching that title. You can find it on the ACS website and make sure you give it a read. We can give Jack a couple more clicks, which I know he'll appreciate. Another reason why you might not want to use TLC anymore is some of your samples won't appear in UV light, so you can't calculate that retention factor. It's also time consuming to create those different solvent systems. All those different percentages of your strong solvent and your weak solvent can become really tedious. So this is where the focus generator comes in. You are going to run a gradient from 5 to 100% of your strong solvent, and you're going to look for where your compound elutes within that gradient. So you can already see how your compound is going to interact with your stationary phase and your mobile phase, and you're going to see where you expect your compound of interest to elute within that strong solvent, what percent of that strong solvent your compound is going to elute in. So this is going to decrease the time you have to spend in method development. It's going to increase the amount you can load onto your columns. It's going to increase your resolution, and it's going to save you both time and money. And the nice thing is now it's available on our CombiFlash Next Gen units. So how do you run the focus gradient generator? Well, the first thing you need to do is select which column you're going to use. Now, I would recommend running a small column for your scout run with a small amount of loading. This is because you're just looking at where your compound elutes amongst the scout gradient, how it interacts with the stationary phase, how it interacts with the mobile phase. You're looking at that retention factor, but you're not looking at it on a TLC anymore. Instead, you're looking at it in a gradient. So once you select which column you're going to use, you want to select the Scout button, and that's the one that Ready is pointing to right there. You don't want to select default, you don't want to run HPLC focus, you want to run Scout. So once you select Scout, a gradient should pop up, and that's going to be from 5 to 100% solvent B with 100% isocratic hold at the end there. So once that pops up, select Start, and the minimum run requirements will pop up. And you're able to choose which sample loading you're going to use. A lot of the time you're not going to select none or on column because your sample is not on there yet. The most common two are going to be liquid and solid. So decide which sample loading you're going to use, whether you're going to use liquid or solid, select that, and then you can press OK. So once equilibration is done and you've loaded your sample onto the column, the scout run will begin. In this example here, our scout run is complete. We did a scout run with 2 different compounds, and you can see here that we're not getting the best resolution between those 2 compounds. So from there, we want to select focus gradient down in the bottom right, and that's what Ready is pointing at right there. And once you select that, the focus gradient definition screen will pop up. And on this screen, what you want to do is select which compound or which peak you want to focus your gradient on. So all you're going to want to do is touch your finger to the screen, and you can click and drag which peak you want to focus on. So that you want that red line to focus on the apex of that peak you want your gradient to focus on. Another thing you can do here is select whether you want to do liquid or solid loading for your focus gradient. So this screen right here, you can select if you want to add a solid load cartridge for your next separation for that focus gradient separation, or you can just select none or liquid loading. You can also change which column you're going to use, the column size in that lower left drop-down menu. Once you have whether or not you're going to do solid or liquid loading and you've selected which column you're going to use, you can select focus, which is what Reddy's pointing to right there. So once you select focus, the focus gradient should appear. So you can see in this example here, the focus gradient is going from about 70% solvent B up to 90% solvent B over a course of 12 column volumes. And you can see our two compounds, how much better they have resolved. We see increased resolution with the focus gradient compared to what we saw in the Scout gradient. So you can see here how the focus gradient generator is saving you so much more time compared to TLC or other method developments, because we just run two runs here, two different separations, and we're already starting to see good resolution and good separation between our compound of interest and any impurities or other compounds we have within our mixture. Here's another example of how the focus gradient generator can just save us time, save us money. We have a mixture of phenacetine and benzyl benzamide, which we separated on our ReadySep Gold 5.5C18 column. So here is our Scout run with this different mixture of these two compounds. And you can see where these two compounds are eluting. And you can see the resolution between these two peaks. We're not seeing the greatest separation between these two peaks, but we are seeing baseline resolution. But what happens when we decide to run this on a focus gradient? Here is our focus gradient from the separation between phenacetine and benzyl benzamide. You can see that the gradient is going from 50% solvent B up to 70% solvent B over a course of 12 column volumes. And you can see how much better our separation is between those two peaks. We're starting to see really good resolution thanks to the focus gradient generator. And with this separation, since we have so much space in between those two compounds, we can increase the amount of loading we do on that column. So we can limit the amount of runs we have to do, we can limit the amount of solvent, and we can limit the amount of time we're working on this separation. So that's going to save us time, that's going to save us money, that's going to lead us to better chromatography, and that's what all of these 5 essentials are for. It's going to save you time, it's going to save you money, and these 5 essentials are going to lead you to better chromatography. So in review, what did we talk about today? Well, we talked about the top 5 essentials that are going to maximize the amount of savings you can do, the top 5 essentials to maximize the use of your time, and all of those are leading to maximizing success in flash chromatography, which started with the stationary phase. We talked about the different chemistries and how different chemistries can have different affinities for your compound. So now we have a better understanding of how different compounds are going to interact with different stationary phases. We also talked about the mobile phase, talked about the difference between normal and reverse phase. We also used an example with that solvent selectivity chart. So now we have a better understanding of how our compound can be carried throughout the stationary phase. We talked about method development, how we can go from a TLC plate and transfer that over to flash chromatography. We talked about isocratic runs, gradient runs, and we talked about stepped gradient runs. We also talked about the difference between liquid and solid sample loading. And then lastly, we just covered the focus gradient generator and why you guys should be using that and how you can use it to save you the most time, save you the most money, and just lead you to better chromatography in general. And with that, that will conclude today's webinar. Make sure to follow us on the medias. We're on Facebook, we're on Twitter, we're on LinkedIn, we're also on YouTube, and this is where this webinar will be posted along with all of our countless other webinars. So it's a really good source of information. Just Google Teledyne ISCO YouTube and you will pop up to our YouTube channel where we have all of our different webinars on there. A really good source if you have any questions, chromatography. Visit our YouTube channel. There's plenty of different subjects getting covered on our YouTube channel. So give that a look. And with that, we can open up the floor to any questions that you guys might have.